Hello, it's good to see you. I hope you're enjoying the restoration of my vintage Heathkit PS-4 high voltage power supply. If you're new to this series, this is a multi-part project, and if you haven't already seen part 1 or part 2, I've included links to them in the description section below. As a recap for what we did in part 2, we did an initial power soak on the PS-4 power supply at reduced input voltages to give those 60-year-old caps a chance to reform. They were kind of scary looking to me, but anyhow, we were able to work our way up to rated input voltage. When we got to rated input voltage, we then took the power supply to rated B+ and C- output voltage at no load conditions. Buoyed with the false confidence of our limited success, we then took the power supply to rated B+ and C- output voltage at rated load conditions. Now that was scary, and everything seemed to work perfectly. I have to admit, I was really impressed with the way the test was running and how smoothly everything went up to that point. And I want you to notice that I didn't say anything about it at the time because I knew if I did, that things would immediately decline into a death spiral. So you got to know when to keep your mouth shut. One thing we did notice during the testing was that the B+ output current meter was dead. And I spent way too much time screwing around with it, trying to figure out what was wrong with it before I admitted defeat. I'm currently looking for a replacement, but that's not going to hold up the restoration of the rest of the power supply. And to wrap things up in part 2, we checked the output voltage of the two OA2 voltage regulator tubes, and we did that right in circuit. So they were under their normal operating conditions, and they appeared to be working pretty good. So that's a good sign. 2 less things that we need to buy, right? I left off by saying that I was going to replace the capacitors offline so that it would be all done for the next part. And the next video, or this video, would be the final installment. But I don't think it's going to be. So I'm going to call this part 2.1, so I can still make sure that part 3 is the final installment. I'm going to give you a progress update, show you where we are in the restoration and how we got here, and I think you'll find it to be useful information. I'm Steve. Welcome to my lab. So in this video, we're going to start by talking about what I did to get ready for the project. You know, just so you can see what my thought process was. And, you know, maybe that's good, maybe to help you. Maybe it's an example of what not to do. I don't know, but you can draw your own conclusions when you see it. So we're going to, you know, go through some of the paperwork. You know, how did I figure out what I was going to do, or figure out how I was going to flub my way through it. So I think you might find it interesting. Then I'm going to show you modifications and updates that I've already made. In particular, we're going to talk about the B+ high voltage power supply. I had to do some pretty radical changes to that. I'll show you what my thought process was for that and what we wound up with. We're going to talk a little bit about, if you remember correctly from the last video, the C-, the voltmeter was reading the wrong voltage for the C- power supply. It was also reading the wrong voltage for the B+ power supply. But today we're just going to talk about the C- power supply voltmeter reading. I put in a little calibration circuit, and I'm going to share with you what I did there. I'm going to talk about the negative voltage power supply and the B+ bleeder network. Now, if you don't know what those are, I'm going to give you a little discussion on how each of those fits into the power supply, what it does, some of the thoughts, design thoughts there, and what I actually found with the components and why I changed what I changed. So again, I think that'll be interesting for you to see. And then you know, I'm going to talk a little bit about some of the testing I did after I made these changes. You never want to go in and change a million things and then power it up. And, you know, when you change when you change 10 things before you do any testing, when you turn it on and things don't work, you're really not sure whether, you can't be sure where the problem is because you've changed so many things. So what you want to do is you only want to change a couple things at a time and then do some testing. Because I was mostly in high voltage circuits here, I'm going to tell you how I tested those to make sure that that something didn't blow up in my face or that I didn't get injured. It's really pretty straightforward. And again, I think, it'll be a good learning experience, if only to say, that's not the way that I want to do it. That works for me too. So anything I do today or any other time, if you have some comments, better ways to do it that you want to share with everybody, feel free to jump in, drop a comment in and let me know what you think. So without further ado, let's get to it. I see you rolling your eyes and saying, but Steve, I've got this covered, but we're going to go through this anyhow. Not only are we probing around in deadly high voltages, we're actually making modifications there too. Small slip-ups can go seriously wrong very quickly. If you don't know what you're doing, stay the hell out of it. If you're following along, you are doing so at your own risk. If you're not comfortable with what we're discussing or lack the tools and safety equipment to safely proceed, don't do it. If you decide to go ahead, if at any point you have doubts or concerns of what you're doing, you should immediately stop, unplug the equipment, and call a knowledgeable friend or professional for help. I want to see you here for the next video. Be safe. I want to share with you what I did to get ready for this project. I know some people out there can just jump right in and tear things apart and they don't have any problems. I can't work like that. I usually put together quite a bit of information before I even start to take anything apart. And I always start off with a nice big schematic, something that I can draw on, write notes on. I have a couple of copies of this always at my desk, so I can always quickly access it, and it's a good size one, so I can put big notes on it and keep all my thoughts together. I also have, I try and purchase an assembly manual. I have an assembly manual for this PS-4 power supply, and they seem to be pretty rare, so I was lucky to get a copy of one. And in there was this picture of what it looks like under the chassis. So I printed this off. Again, I always like to work on big paper. My eyes aren't that good. And if you notice, I've labeled all the components so that I can quickly, identify what part is what looking in the bottom of this chassis. And, I have to go back and forth to make sure that I identify the part right. But makes life a lot easier when you're troubleshooting or looking for something. I also take the parts list, and you're going to love this one, right? This is a true engineer at work. I make a spreadsheet of all the components that are in the project. I have, what the values are, what the manufacturer's part number is, what are the characteristics of the part, what I measured when I took the part out, what I'm going to replace it with, where I'm going to buy it, how much it costs, all kinds of shit here, right? So there's quite a bit of information. This one is a 3-page part list. Again, notice it's pretty big because I like to see things big. Makes it easier for me to keep an eye on it. I then get any information that I can, and I try and figure out, what's going on in the circuit. And again, I like big pages because I can write notes on them and figure things out. I might go back and change some of the notes, just for scratch sheets. I might zoom in on some of the pages so that I can write more specific notes of what's going on there. So I think that's kind of important as a starting point, and I'll do probably 90% of that. I might take the covers off and take a look inside just to start to familiarize myself with what's going on inside. But I always like to have a lot of notes and a lot of paper that I can scratch on. And I'm going to show you a couple of other instances where I've used notes and scratch sheets before I've dove into something in this video. So let me know what you think, all right? So today we're going to talk about 4 of the modifications and updates I made to my PS4 power supply. And here's how we're going to do it. We're going to start off with a schematic like I'm showing you here right now. And by the way, there's a link to this schematic in the description section below, so if you want to grab a copy of it and follow along at home, feel free to do that. Anyhow, what I'm going to do is I'm going to, on the schematic, I'm going to circle the area that we're going to be talking about, where the update or the modification was made. I'm going to talk a little bit about what's actually going on in that section, how that system works, not in a lot of detail, but just give you an idea of what's going on. I'm going to talk about what I found when I measured the components and why I decided to make the changes that I made. I'm also going to talk a little bit about testing. I did some testing after I completed the modifications. Some of the testing I'm going to talk about while we're talking about that section. At the end, I might talk a little bit more about overall testing, but it's important to test what you're doing as you're going along, so you don't lose track of where you are. If you change too many things at once and you go back to test it and things don't work, it makes it a lot harder to troubleshoot. So I did some incremental troubleshooting, so you can kind of see what my thought process was for what that's worth, and we can go from there. Now, after we review the schematic, I have this picture of the bottom side of my PS4 power supply chassis, and for orientation, the top side of the picture is the front panel. The bottom side of the picture then is obviously the back panel. You can see the fuse holder at the very bottom. What I'm going to do is I talk about each section. I'm going to circle where the parts are on this drawing. And I'm going to show you a before and after shot, right? Because I have a shot of the chassis after I made the modification. And we'll be able to see what it looked like after I made the modification. All right, so I think it's a good way to do this. Let me know if it's helpful, if you like the way that I'm doing this, or if you think there's a better way to do it. So I want to make it useful for you and for me. Let me know what you think, all right? The first update I did was to the B+ high voltage power supply, which is shown circled here. Now this power supply supplies raw voltage to the 2 series regulator tubes. And the 2 series regulator tubes then will output a voltage, based on what we set the B+ adjustment knob to on the front panel of the power supply. The voltage here is 600 volts. It's a pretty simple circuit. It's a full wave voltage doubler. I think it's a Delon type of voltage doubler. I believe that's what it's called. And what it does is alternately it'll charge up 2 caps. We see we got 2 caps in series here, and what we're doing is for one half of the cycle we're charging one of the caps to 300 volts. For the other half of the cycle we're charging the other cap up to 300 volts, and because the 2 caps are in series we wind up with 600 volts on the top of both of them. It's a pretty simple circuit. Voltage doublers were used in many places, probably primarily where you might see them would be like in a TV where we needed really high voltage for like a flyback transformer application where we needed a couple thousand volts. What it allows us to do is it allows you to use a cheaper transformer, a lower voltage rated transformer, and get double the voltage out of it. So it's a pretty nice circuit, pretty simple, been around for a very long time. If you notice the diodes, we see 2 diodes in series for both the positive and the negative rectification. And the purpose of that is, this thing was designed back in the late 50s and early 60s, and there was some concerns about the reliability of silicone diodes, silicone rectifiers, solid-state rectifiers at the time. So they were worried about them failing. So the way they kind of got around the problem was they would put 2 in series in case one of them failed. Presumably the other one would still be working. Because they're identical diodes and they probably came out of the same manufacturing lot, I don't know how long the second diode would last or how you would know that the first one failed, but that was kind of why they used 2 of them. And you'll see that in a lot of places in older equipment. Why are there 2 diodes in series? Because they were worried about one of them failing. And the predominant failure mode of a diode is shorted. So we don't want to cook anything, so by having 2, presumably we're safe. And so that's what they were doing there. Now, as you look at the capacitors, I did some testing on them, and they're kind of interesting. They're 350 volt capacitors, working voltage, but they have 300 volts across them, so they're pretty close to their rating. And when I tested them, they were both overperformers. One of the 70 microfarad caps was reading just a little bit below 100 microfarads, and the other one was at 85 microfarads. So, that's not unusual, and that's, probably well within the tolerance. Typical tolerance on electrolytic capacitors is pretty wide. One thing I did notice, though, was the leakage of these capacitors, and I tested them at their working voltage of 350 volts. C3, the leakage current was 11 milliamps, which is pretty high, and C2, the leakage current was 10 milliamps, which is almost as high. So, even though it appeared to be working right, I think these caps were, on the way out. So I replaced them with new caps. Same thing with the diodes, because they're so old. They're really cool. They're ceramic diodes, much larger than, diodes today. And I was a little nervous that, they might have been getting close to the end of their service life, particularly because they're hooked up to a transformer that you can't replace today. You can't buy a replacement. I decided to change the 4 diodes and the 2 capacitors. And actually, I probably could have just used single diodes, one for the positive, one for the negative. But I actually put in diodes in series again, just because diodes are cheap. So, all right, so let's take a look at what we wound up with here. Now, here's what the circuit originally looked like. So you can see the 2 big 70 microfarad caps and the 4 diodes. Those are those white ceramic things. I drew it up schematically, but kind of the way it's physically wired. And the reason I did that was because I was changing the components. I wanted to make sure that I understood how the thing was wired in, what was where in the circuit, accounting for any wiring that's hooked up to it. Like, for instance, if we look off the top of diode D3, which is the top diode in the schematic, it says it goes to V5 pin 3, all right? And V5 pin 3 is the plate on one of the series regulator tubes, the 6L6s, and then it crosses over to the other series regulator, right? So, I wanted to make sure I understood where all the wires were coming from, what the polarity of all the diodes were, what the polarity of the capacitors were, just to make sure that I got it right, when I changed everything. As far as the transformer hooking up, it really doesn't make a difference, which blue wire you hook up where, because it's an AC signal. It'll still work properly. So, I wasn't too nervous about that. But everything else, we need to get right, especially because we're winding up with 600 volts at the end. So, any screw up here could be a nasty explosion. So, I want to talk a little bit about the pots. One of the wires I said lands on pot R22 pin 1. Down at the bottom of the drawing. Talk a little bit about convention of potentiometer lead numbering convention. When you look at the control knob end of a pot, so I'm looking at the traditional pot that's on the right hand side. The leads are typically numbered the way I'm showing there, 1, 2, 3 from left to right. Schematically, you'll see pots drawn the way I've drawn it on the bottom, where the leads are numbered 1, 2, 3, from left to right, where 2 is always the wiper, the moving part of the pot, and 1 and 3, the way they're chosen is when you turn the knob, when you look at the knob from the front end, the control knob from the front end, and you turn it clockwise, the wiper will always move to make the resistance between 2 and 3 smaller, or alternately, the resistance between 1 and 2 larger. And I'm going to say that that's, I dare say it's a convention because I know somebody's going to challenge me on it. So it's a good rule of thumb. I'm also showing like a little trimmer pot because I used a couple of trimmer pots for some of my modifications. And their leads are the same way. The leads are numbered. If you look closely at that trimmer pot, you can see that they're numbered on the body of the pot itself. But the same convention holds. When you turn the control knob clockwise, and by the way, that's a 20 turn pot, that blue thing. When you turn it clockwise, you're going to move lead 2 towards lead 3. So the resistance between those 2 points will decrease. So just kind of remember that. You'll see lots of places, you'll see pots numbered. And if you're wondering what the numbering means, even on this schematic, the pots are numbered, what lead is what. And here's a way that you can identify, what they're talking about there. So, all right. So here's the finished product. You can see that I put in 2 new 68 microfarad caps. I couldn't get 70 microfarad caps. So 68 is pretty close. And these are 450 volt working volt caps. You can see they're a lot smaller than what was there. And I put in radial lead rather than axial lead. The way I did this was I got rid of all of those white ceramic diodes, and I kind of wired it up on 2 terminal boards. And you can see that, how I wired the diodes. I wanted to make sure that I had the polarities right, make sure I had the wires landing in the right place. And I drew it this way so that it pretty much looks exactly the way it does when it's installed, the way I drew it, right? So this way I can, glance at the banding on the diodes and make sure that I had it right. Next shot here, I kind of show a close-up of what the circuit actually looks like. Came out pretty good. Now the diodes that were originally in there, those big ceramic diodes, were 500 milliamp, 600 peak inverse voltage diodes. I replaced them with a 1N 4007 diode, which are 1 amp 1000 volt peak inverse voltage diodes. So they're higher rated diodes. I probably could have got by with 1 in each leg, but I decided to put 2 in because, diodes are, they're like 39 cents each. So it worked out pretty well, and I was able to clean up quite a bit, as you can see here. Easy modification. When it came to testing this, because it runs at 600 volts, you don't just put the voltage to it. I actually hooked it up to my isolation transformer in Variac, and I actually did a lot of testing at like 5 and 10 volts AC to make sure that I had all the polarities right. Just barely sneaking in some AC voltage so I can make sure everything was okay. And then I brought up the voltage, slowly, just to make sure that I did have the polarities correct. If you check the polarities at 10 volts and you go, oh yeah, I'm cool, you want to make sure, just don't put the power to it. Just take a couple of extra minutes and you'll be a lot safer that way. All right. At the same time I was working on the high voltage, the B+ high voltage circuit, I decided to see what I can do to improve the reading, the voltmeter reading for the C- voltage. If you remember when we were doing our testing, the C- voltage was reading a little low. This circuit actually sits up behind the B+ high voltage circuitry, so I figured I would go after this at the same time, get in there while I can, make this modification. This is pretty simple. So what happened was, is we read the voltage through a precision resistor, R25, here circled in green. It's a precision resistor, 1% resistor. And what that does is that sets up a current flow for a 1 milliamp meter that's actually, it's marked off in voltage, right? So current flow through that resistor is equal to voltage. And I can calibrate the milliamp meter to read voltage based on the current flowing through that R25 resistor. When I measured R25, it was 1%. It's a 1% resistor, and it was off by a little more than 1%. That wasn't accounting for the big discrepancy in the reading. So I think the meter's a little tired. I should run a calibration on the meter, and maybe I will in a future video just to show you how I would do that. But what I decided to do was to make that circuit adjustable, right? Because that resistor is just setting up a current flow based on the value of that resistor. What I did was, oh, by the way, before we go to that, there's the resistor. You can see it sitting behind the diodes, the original ceramic diodes for the B+ high voltage section. And that's kind of why I went after that, get everything, while everything was out of there. This was an easy modification to make, and this just kind of shows where it's located in the chassis. So what I did was originally, like I said, R25, it's 150K ohm, 1% resistor, sits between the meter selection switch SL on pin 6 and the binding post, B7 binding post. B7 binding post is the red binding post for the C minus output voltage. So it's, it's reading that voltage through this resistor, goes to the switch then switches it up to the meter to read. Right? What I decided to do was I took that 150K resistor and I replaced it with two resistors in series. One resistor is a 100K ohm resistor, and then I also, in series with that, I put in a trim pot, a 20-turn trim pot, 100K, and what that allows me to do is when I center up this trim pot at 50K, I wind up with 150K like I originally had, and now I can turn the pot to change the calibration on the voltmeter for the C minus reading. So that works out pretty well. I chose the way that I wired this so that when I turn the pot clockwise, the meter indication will increase, right? That's always a good idea. That's kind of intuitive, right? You want to turn, when you turn a pot, when you turn something clockwise, you want to see it increase. When you turn things counterclockwise, you want to see them decrease, right? That's kind of a normal convention. And I chose the pot so that I should wind up with about, plus and minus 50 volts of adjustment range. Obviously, I don't need that. If I remember correctly, we were off by like maybe 15 volts or something like that. So it should be well within the range of this pot. So we'll see how that works. Now this is what it looks like wired in place, and you can see, you can see the resistor, the new resistor, the 100K is pretty prominent on there. Wiring back to pin 6 on meter switch SL, and it wires up to B7, which you can't see. It's kind of hidden behind that orange capacitor. So this should work pretty good, right? But I can hear you saying, isn't that adjustment kind of close there to that power supply terminal for the B plus high voltage? And, there's 600 volts there. That doesn't look good, does it? Well, it turns out I wasn't thinking ahead when I put that there. I should have, because I mounted it before I mounted the terminal boards, and it wasn't until I had everything in place. And then I went, oh, geez. So that adjustment pot is like dangerously close to 600 volts. There's 600 volts on the terminal circle there. I took this picture with my screwdriver in the slot there, and the circuit's de-energized. You really need to really think ahead when you're doing these things, and I wasn't thinking. So obviously I can get around this by putting lots of shrink tube around the body of the screwdriver, but you need to be really careful and always realize, always look at what you've done and make sure that you're not going to get in trouble if you're probing around in there. So a little bit of stupidity on my part, but that's okay. Do as I say, not as I do. By the way, the B plus voltage was also reading low, and we're going to do a similar modification, with its calibration resistor. I'm going to put a pot in series with a new calibration resistor so that I can adjust the voltage on that indication too. We'll see that when we get there. That'll probably be in the next video, though. The next thing we're going to talk about is our negative voltage power supply. Now this power supply supplies raw negative voltage to quantity 2 OA2 voltage regulator tubes. Those are 150 volt voltage regulator tubes that are stacked one on top of the other. And what that allows us to do is to take the raw voltage, the raw negative voltage, which is on the order of about minus 340-ish volts, and it'll regulate it down to minus 300 volts and also minus 150 volts. And that voltage is used for a variety of biasing references, and it's even used for the C minus voltage output. So it's kind of an important supply. The supply consists of a dual diode rectifier. It's a full wave rectifier that's charging up two smoothing circuits that consist of C4 and C5. Well, part of the circuit that we're concerned with is circled in green. This is the circuit that actually sets up minus 340 volts for our 2 voltage regulator tubes. As I checked these components, they were in pretty tough shape, considering the way the power supply was working. For instance, C5, which is the 40 microfarad cap, the second cap, the cap to the right, that had a leakage current of 22 milliamps at 425 volts. That's really bad. That's really bad. It tested out at 47 microfarad, which isn't too bad. That's well within the range, but the leakage was off the scales, right? Capacitor C4, which is the 20 microfarad cap, the cap to the left, that had a 4 microfarad leakage. It tested out at, it's supposed to be a 20 microfarad cap, it tested out at 26 microfarad. That's not bad, that works. But again, the leakage is kind of high there. The real problem in this circuit were the 3 resistors, R19, 20, and 21. Now R20, which is the resistor that sits between the 2 capacitors, capacitor C4 and C5, that's supposed to be a 1.5K 2-watt resistor, and it actually measured at almost 3K, right? So it was off by almost 95%, which is crazy. And that's a current limiting resistor for charging up C5, right? So that would really affect the operation there. The other 2 resistors, R19 and R21, weren't in too good a shape either. They are specified as 10% tolerance resistors. R19 was at about 20% out of spec, and R21 was just about 10%. So I decided to change all of those. And by the way, those are R19 is a 1-watt resistor, R20 and R21 are 2-watt resistors. So I decided to change those, and I upped them to the 2 2-watt resistors, R20 and R21. I made those 3-watt resistors, and R19, which was originally a 1-watt resistor, I replaced it with a 2-watt resistor. Here we are showing where the parts are in the circuit. They look like they were in pretty good shape. You'd expect to see maybe some distress or some overheating. The resistors all looked pretty good. I was pleased with the way they looked. And actually, like I said, it worked pretty good. So I was surprised when I checked the condition of these parts, the way things actually checked out. This next slide shows what the replacement looked like. It's a little bit cleaner. Obviously, modern resistors and capacitors are much smaller than 60-year-old components. So we're going to zoom in on this a little bit. This is what it looked like when I wound up changing them. I was able to move some of the terminal boards around. For instance, the terminal boards at the positive end of the capacitor, there's a terminal board there off to the left. Originally, that was like really close to the sheet metal, even though that's a common. That's a circuit common. It was a little bit too close for my taste to the sheet metal. I was actually able to turn that around and get it a little further away from the sheet metal using the original mounting hole. We can see the resistors I changed, the 2 black resistors. R20 is that black resistor that hangs on the terminal board at the negative end of the capacitors. And it came out pretty nice. I like to use a lot of shrink tube, protective tubing on my resistors, any place they can short out. So you'll see that, in quite a few locations. So this came out pretty good. I was pleased with the way this came together. The final thing we're going to talk about today is the B+ bleeder network, which is shown, circled on the schematic, and I've blown it up here. And this is actually 4 2-watt 27K resistors, and they run between the B+ output and the minus 300 volt reference from that negative power supply we were just talking about. Now what these do is they put a load on the series regulator. The series regulator needs a minimum amount of current drawn from it all the time in order for it to control properly. If you use the nominal value of these resistors, the 27K, and you calculate, what would you have at 0 volts, you see, it's only a couple of milliamps that this draws. But the problem is with this bleeder network is it's always hooked up, and when you bring the B plus voltage up to 400 volts, there's 700 volts across this voltage divider. And if you calculate the power that's being dissipated in each of those resistors, they're 2-watt resistors, but we're dissipating about 1.1 watt in each of those resistors. So they're probably running pretty marginal there. When I checked those resistors, they were all running a little high. They were just about at the limit of their spec. They were running, in general, about 9% off their nominal values, which means that we would pull less current down the net through that bleeder network when we were sitting at 0 volts, to maintain the stability of the circuit. So what I decided to do is I decided to change all 4 of those resistors. And I replaced those resistors with 2-watt resistors because that's all I can get. Now, if you're wondering why there's 4 resistors here, I'm thinking that that's what they had in stores, in the warehouse, right? That was a big thing at Heathkit was, use what you have in the storeroom, right? So they needed, resistors that had, some realistic wattage, something that they might have in the storeroom. And they probably stumbled across these 2-watters, and they said, oh, that'll work, all right? Now, if you're wondering why you couldn't do it with one resistor, there's a couple of reasons. One, it would be a 10-watt resistor. You'd probably have to put in a 10-watt resistor. And with 700 volts, it's kind of hard to find a resistor, a 10-watt resistor with a 700-volt rating. So, you'd probably need at least 2 resistors. And if you had 2 resistors, they would have to be probably 5 or 10-watt resistors anyhow. So, again, this is probably what was in the storeroom. That's what they went with. That's what we're going to go with. We're going to go with the same thing in its place. Here's where those resistors are located, or where they were located in the original scheme of things. Again, considering these resistors were probably running, at over 50% of their rating for at least some amount of time, I would imagine. No signs of distress at all. I mean, they look pretty clean, right? So here's what it looked like when I changed them. Again, these are 2-watt resistors. I was able to clean it up and open up quite a bit of space there. When all was said and done, like the B plus power supply, I also tested this circuit for output voltage and polarity. So I brought it up very slowly. I brought it up at the same time I brought up the B plus. So I was able to do a bunch of tests on it. Here, obviously, I didn't change any diodes, but I certainly wanted to make sure that I had the proper polarity on my capacitors, while the voltage was still below the 340 volts that they normally see. Again, brought it up in steps. Initially, until the dual diode rectifier, that tube, that 6x4 tube, went into emissions, I was seeing some strange voltages, a couple of volts opposite polarity across the capacitors. I stopped a couple times to check to make sure the wiring was right. When I got the voltage up to about 60 volts, the polarity on the capacitors changed. I never saw more than about 4 or 5 volts opposite polarity across those capacitors, so I didn't think it was anything to worry about. And that's where we are. As you can tell by the messy bench and the underside of this chassis, things are moving forward. I think we have 2 more videos to do on this series though. In the next video, we're going to cover the final modifications and updates. And then the video after that, I think we're going to power it up and put it through its paces and see what improvements we made, if any, because it certainly was running pretty good. So anyhow, I got a bunch of interesting projects coming up. Hope to see you for all of those. Until then, be safe.